I want to state another lemma before proving that the definition of integrability I gave at the very beginning of this session and the one I gave in most recently with the mark partition are the same. I need also this lemma, which is actually here not very deep lemma either. It has nothing to do now with the characterization of the supremum or the infimum, but it's something extremely technical. I could have left this as an exercise, but it would have been seen as a bit weird. So, but you will see, hope you understand, there's absolutely nothing deep in this lemma, but I need it. Okay, so assume that I have a partition on the interval AB, as usual, right? And this partition is marked by points anywhere they say, anywhere you say, it doesn't matter. Now what I'm going to do, I'm going to add another point in the partition. So pay attention, there is the point of the partition and the point of the marking. So the point of the marking, all of them won't change except maybe 2. I'm going to be more specified. So P2 is just the same as P1, but I add 1 point C in between. You have the right to say it's in the middle, it doesn't matter, actually. But it's different than the one, let's say a priori it's different than the one here, because if it's the same, well, I won't do anything. That's right. Alright, so I designate actually the integer k, between 0 and n minus 1, such that c is in between xk and xk plus 1. And I'm going to now mark, so P2 is well defined, it's just a, x1, x2, xk, c, xk plus 1, and so forth. So this is something quite clear to understand for the partition. Now, how do I mark P2? I'm going to mark P2 like this. The same marking, pretty much all the same marking as the one for P1. So x0 star, x1 star. I stop as right before xk star. Xk star is somewhere here in between for the marking of partition P1. But I don't take him. No, I will take y and z, where y belongs to xkc and z belongs to c xk plus 1. Y and z can be the same, it doesn't matter. Right? And then after that, when it makes sense, when if really k plus 1 is less than n minus 1, otherwise this wording is empty, that means that k minus 1, k was equal to n in that case, and then in that case, so k minus 1, yeah. So so k was equal to n, then in that case the y and z are the two markings, so c was a point between xn minus 1 and b, in other words. But it could be that this is empty, but in general you don't expect these things to be empty. But this is the way, let's say, I mark the partition. So this is the picture I want to show you. Here are the initial partition P1, 0a, x1, x2, x3, x4, b. So I do it, you see, for only 4 intermediate points. Here are the marking, x1, 0 star, x1 star, x2 star, x3 star will be here, somewhere in between. It doesn't matter, x4 star here. And then, you know what, I insert a point C in the middle of the interval, different than A, different than B, different than any of those xi here. And and I choose 2 points, one on the left of C, but after x2, and z on the right of z, but on the left of x3. So I have a new partition, and now I'm asking myself the following thing. This is what the lemma state. Assume that I take a function which is bounded on this interval, not necessarily remain integrable. Here I'm not necessarily stating that the function is Riemann integrable. I don't care about that for the moment. But I want to say, what is the mistake I do by adding a point to this first partition? Well, the answer is simply like this. If you take the Riemann sum of f associated to P1, the marked P1 partition, and look at the difference between the Riemann sum associated with P2, marked again, well, it is bounded by 3 times the bounds for f time the mesh of P1. Right, so this is a lemma which is extremely technical, but we will need this for the proof of the theorem. Alright, so let's prove this lemma. So I need to erase some place here. Upstairs. Well, you know what? The best thing to do here in this case is simply to write what is S of P1 and what is F of P2 and where do I locate the difference. Okay, so what is SF of P1? SF of P1, let me rewrite SF of P1 like this. This is the sum from J equals 0 to K minus 1. I do it purposely, you see. I'm going to say pretty much the same thing I did in the first place when I showed that a partition which is finer than a former. Then the UFP was less, the UFP prime was less than UFP, and the LFP prime was bigger than LFP. This is pretty much the same proof I'm going to follow. So here I don't like the way it looks like. Sum from J equals 0 to K minus 1 of f xj star xj plus 1 minus xj plus the sum from j equals 0 to, no, not j equals 0, j equals k plus 1 to what is it, n minus 1. So whenever this sum makes sense, of course, it could be that k minus 1 reach already, that k is equal to n, then I already have made the sum up to n minus 1. Exactly the same thing I said earlier. So f of xj star xj plus 1 minus xj, and then let me write what is missing here. It's exactly when j equals k. That was I said. So this is plus f of x star k times xk plus 1 minus xk. All right. Now let's write what is S of P2. Well, S of P2, you will see that we have indeed two more intervals to consider after those ones. So SF of P2, since these are guys from the same mark partition, they also belong to the same partition, this sum remains the same here. I mean, at least the beginning. So that remains the same, because this xj star when j is less than k not more than k minus 1 and not less than k plus 1 are part of the second marking times xj plus 1 minus xj, and then I need to add the two things which are missing, this bit and this bit, together with the marking. So I have two more terms here to add, plus f of the first one, which is y, times x, so it's not x, but c minus what? C minus xk, plus, let me write it here, f of z times xk plus 1 minus c. So now I can probably erase everything here. And now let's make the difference between those two guys and put the absolute value. So SFP1 minus SFP2 in that case will be less or equal than, well, you see, will be equal, sorry, I should say equal. Well, if you, first of all, equal, so because it's really an equality at this beginning. So this term minus this term minus this term go away. The only thing that remains is the difference between this sum and this guy and the sum of those two guys. So we have fk, if f of x star times xk plus 1 minus xk minus f of y c minus xk minus f of z xk plus 1 minus c. That's not a nice k. Alright, and we take the absolute value. Alright, so I think I can erase at least that part. So this is what I want to show. Well, now we can say, well, whether the absolute value of the sum, because it is the sum if you want, and the difference is also a sum, is less than the sum of the absolute value. So it's not very a smart estimate, because you see, I could say, well, maybe I could say something, all those two things cancel out. No, I don't want to do that. I'm just saying this is equal to f of xk star times xk plus 1 minus xk plus f of y times c minus xk plus f of z in absolute value times xk plus 1 minus c. And now I think you see where the 3 comes from, because we have 3 terms. So this is all less than m. This is less than the mesh of the partition, the first partition. This is also less than the mesh of the partition. Why is that so? Because c minus xk is less than xk plus 1 minus xk. Remember, c is between xk and xk plus 1 by definition. So this quantity here, actually I put it in absolute value, I don't need, this is already something positive, is also less than the mesh of P. Same thing for this guy. And this ends the proof of the lemma. Three times capital M, the supremum of F, times the mesh of P. This lemma has a corollary, which is, I will go very, let's say, I'm not going to do all the details because this is quite easy. I mean, I think we can do it by induction. I mean, you can finish maybe the induction as an exercise, but it's very easy. So, you know what? So consequence or corollary. Assume I'm going to do the same process from P1 to P2, from P1, P2, P3, P4, Pn. We have a finite set of partition such that, in other words, Pj plus 1 equal Pj union a certain Cj, right? And the construction of Pj from Pj plus 1 to Pj is exactly the same as the one I've got from P1 to P2, where Pj plus 1 is constructed like from Pj as P2 from P1. That is, by adding a point in the middle of the partition here and replacing the marking I choose for this interval by two other guys. Well, you do it once, I already did it once, twice, 3 times, n times. And at the end, what you want to do, you want to say, I'm going to say that if f, let f from AB to R, again f bounded by m, then the difference between SFPN minus SFP1 is less than 3m times n, A, yeah, time the width, the mesh of P. Proof, well, proof follows immediately. Actually, I don't need an induction. I can say proof. SFPN minus SFP1 is simply nothing else than the sum, the telescopic sum from J equal 1. So I'm not so sure if it's 1, just maybe 1 up to n. Let me change the index because I'm not so sure. So SFPJ minus SFPJ. It's not written like this. SFPN, let's say SPN minus J. I'm going to start by J equals 0. Minus SFPN minus J plus, so it is Pn minus 1, therefore, yes. Right? And now let me see, so the lower bound is correct because I want to start by Pn. And what is the upper bound? I want the upper bound to be 1, so it's n minus 1. All right. Well, this is true. If I put the absolute value, I'll have the absolute value outside, but using the triangle inequality is going to be less than the sum of the absolute value. But now we have to remember that each of those consecutive guys are constructed from one another in the same way as I did from P1 to P2. So each of those guys will be less than 3 times m times, sorry, I forgot to say, sum from J equals 0 to n minus 1 of 3m times the width of P n minus J minus 1, the one which is, let's say, not finer, but bigger in a way. But since all those partitions are finer, are getting finer and finer, and P1 is the bigger, let's say, the less fine, I should say the opposite of finer, grosser, the grosser one. So I can say that this quantity is less than P1, the width of P1. And of course, this quantity is nothing else than n, so 3 times m times the width of P1. So it's just, I mean, if we understand the first part of the lemma, you understand this corollary quite clearly. All right. So this being said, we are now in position to prove the theorem. So I need probably, for sake of consistency, to recall both definitions and give let's say at least a number or something. So definition 0, because this is where I start with. So f. So let's not give any definition yet. Let's first of all recall the context. F is a function which is bounded from a to b. Take its range in R. Again, f is less than n. First definition. Let me just recall it. F is a Riemann integral if and only if, by definition, for O epsilon positive, there exists a partition P, not necessarily marked, such that UFP, which is defined, which we already defined before, minus LFP, this quantity being always positive, but it's less or equal than epsilon. It's I like this definition because it's compact and we don't need to mark the partition. That's also a good thing. Also, it's related. You could really reformulate this by means of step function, as I said earlier. Definition. I like to call definition 2 because this is not exactly the initial definition that we have in the first place, but this is more the Cauchy one. So, f is Riemann integrable if and only if. So it starts by the same thing. For all epsilon positive, there exists a delta positive such that for all partition P with a width less than delta, and for all the marking you are taking, xi star between xi and xi plus 1, so it's always the same setting. I need to recall this for sake of consistency. So it's for it. So it doesn't depend on the choice of the partition as long as the mesh or the width of this partition is less than delta, and it doesn't matter whether where you have chosen your marking. In other words, all right. So for all P1, so actually I have two partitions. I need to take two partitions. For all P1, P2, with the width of P1 less than delta, the width of P2 less than delta. And for all xi, it doesn't matter which marking I take. So marking P1. And I will say y star, no, so it's the same thing, sorry. I know it's another partition, so yeah, so I need to put yi star, yi plus 1, I equals 0 up to, not, so it does not necessarily mean that this is the same coordinality, so I have to put an m minus 1 here. So here in the settings we have P1 equal x0, x1, so this is A of course, xn minus 1, this is xn, this is B. And P2 is equal to y0, which is again equal to A, y1, ym minus 1, and we finish by ym, which is equal to B here. So this is for the definition. It's a bit, you know, a lot of wording, but just for saying, take two marked partition P1, P2. They don't need to be marked by the same point because those partitions actually have nothing to deal together. But what I want to say is, as long as I have a width, they both have the width less than delta, then the Riemann sum associated with f of P1 minus the Riemann sum of f associated with P2 is less than epsilon. Alright. So, what I'm going to do, I'm going to first show, so there is one case which goes better than the other. So, we're going to show two, the definition 2 implies definition 1. It's going to be easier, as if actually that definition gives us a stronger security. But actually, it's not the case because, as I said, the definition 1 will be implied in the definition 2 later on. But we will prove first of all definition 2 implies definition 1, and then we do the opposite.